Okay, people, can you hear me? I hope that you can hear me. Yes, okay.
Yes.
Okay. Right. I think, well, I hope that you can see the program of the session here. I share my screen, this screen with you. So according to this program, I think that everybody's here except speaker number 5, Juan Carlos Rodriguez, who is the penultimate speaker, who I don't think he's here. Is he here? Apparently not. So we can start now. The first speaker is myself, but in case that this speaker, Juan Carlos, has not come until the time that his talk starts, I think it's better if Deborah takes his, if it's okay with you, Deborah, to speak half an hour earlier, and if he comes, then he can speak in your place after that. Is it okay?
It's okay.
Okay. Okay, thanks. So let me now share my talk with you, and I will start. So the idea here is to speak for about 25 minutes, something like this, and leave a few minutes for discussion if there are any questions or some discussion, just 2 or 3 minutes or something like this for each talk. So during every talk, everybody except the speaker has to have his microphone deactivated and also his camera off or her camera off. Okay, so let me start now. If you don't have any other questions or comments, I can start. Okay, so let me start. All right. So I hope that you can hear and see these slides. Now, this is the title of my talk: synchronization of in couple mixmaster oscillators. This actually, this topic is explained in much more detail than it will be given in this talk. In this paper over here. So if you are interested, you can read my paper over here. Now, okay. Now, mainly what I will do is that I will very quickly discuss the idea of synchronization dynamics, which is not a very old, well, topic in dynamical systems. So this is a new approach to the problem of basically understanding the BKL conjecture and related topics. So after I give you some very brief introduction to what synchronization dynamics is, I will talk about the inhomogeneous mixmaster picture according to the BKL conjecture, and especially what we call the evolution of spatial points according to that. And then from 4 until 7, I will just discuss the mixture of the two, synchronization, the possibility of synchronization in homogeneous mixmaster dynamics. Now, this actually approach is quite new, and it has many implications, actually, two of which I will try to discuss in this talk if I have enough time. Anyway, if you are interested in this kind of stuff, you can read my paper, which is shown here on every screen, actually. Okay, so the motivation of this work is, of course, to get a better understanding of the so-called generic nature of the cosmological singularity according to the Belinsky, Kalatnikov, and Lifshitz conjecture. Well, I will explain what this means later. Secondly, to have a better understanding of what it means for the the cosmological Einstein equations to evolve a solution in the homogeneous case near the singularity, in the past singularity, in the past direction. And also we would like to understand through this approach the horizon problem in cosmology, of course, and the problem of entropy, also in a cosmological setting. Now, of course, these are not, all these topics are not new, of course, but here we approach these topics through a completely new, we believe, approach, which is based on the idea of synchronization, which is a topic in dynamical systems. Now, what we are going to do, I'm going to talk about this a little bit, and then see if synchronization can arise in the context of G0 cosmologies, which are cosmologies without, as you know, without any symmetry. Now, by this, I mean, this is another name for inhomogeneous mixmaster dynamics. Okay, let me tell you a couple of things about synchronization dynamics. Actually, this is a topic that appeared in dynamical systems about 30 years ago, about 1990, and by now there are many books on this topic, on separate, with many different applications, from chemistry to physics to biology, etc., engineering. But so the idea is this: since we know so many things in nature that can synchronize, from fireflies to crickets to hard cells, etc., the idea is how can we simulate and explain this phenomena through dynamical systems. Now, there is a method to do this, to examine, that is, to examine whether a system, a dynamical system, can have this property and synchronize. And this is the following. Suppose that you have a dynamical system like this. Basically, what one does is, and this is actually, I will talk about this very briefly, because to explain all this would require another talk, actually. But this sync setup method has the following steps. Suppose that you have a dynamical system like this, that we call a transmitter. You will see why we call it like that in a bit. And then what we do is we split the variables like that, basically mainly arbitrarily, into some variables u, and the rest will be v. And then this splits like that into two parts: one part for giving the evolution of u, and another part, the second part, the subsystem, giving the evolution for the variables v. Now we call this subsystem B, and then what we do is we create an identical system to the transmitter, which we call the receiver, by substituting the variables u prime in place of the variables u, and in the place of the subsystem B, we introduce the variables v prime like that. But look here that we have kept the old variables u, but with the new variables v prime. And then once we have two copies of the same system like that, we get a system that we call a transmitter receiver like this. So we have the u variables are the same, but the v evolution, we have two subsystems like this. Now, of course, we can, in general, we can have these two subsystems, of course, uncoupled. That is, the two identical systems, the transmitter and the receiver, we can consider them uncoupled, but also with some coupling between these, and consider the following. Suppose that we define this, what we call the synchronization function, the sync function omega, which is just the error function v minus v prime. And of course, giving the transmitter, the transmitter receiver dynamical system, we can arrive at a new dynamical system that is obeyed by the sync function omega. and analyze the behavior of this synchronization dynamical equations, that is equations for the omega variable. And then we say that the receiver will sync with the transmitter, which will synchronize with the transmitter, provided omega goes to 0, as tau goes to some limit. Here I use this variable tau because well, this is the same letter with the dimensionless time that we will be using later on for the mixmaster case. Okay, so in case where this error function goes to 0, then of course the two systems just synchronize completely, and then they both evolve in perfect harmony or synchrony, and this is the property of synchronization. Now there are many systems, as I have already said, that have this property of sync, and this is a very important and actually a very mysterious property that many physical systems share. Okay, now this is basically a very, very short and brief introduction to synchronization dynamics. Let me now say a couple of things about the inhomogeneous mixmaster system. Now, it is a basic property of the Einstein equations in the cosmological setting in the inhomogeneous G0 case, that distinct mixmaster spatial points evolve as separate homogeneous mixmaster universes. So each spatial point, you may consider it that evolves as a separate homogeneous mixmaster universe. Okay, this is one of the most basic characteristics of the BKL conjecture in the inhomogeneous case, of course. Now, what it means here is the following. So the best way for the current purposes, the best way to describe this system is by introducing dimensionless, the so-called dimensionless variables. These are very famous choice of variables done by Wainwright and Su 30 years ago, more than 30 years ago, but also this has been used by many groups during the last 3 decades. So one introduces these dimensionless variables n and sigma, that then measures the Bianchi type and the spatial curvature, and sigma plus and sigma minus measure the anisotropy of this is the shear variables, and so they measure the anisotropy of the Hubble flow. Now, so for each spatial point, we have this kind of state vector field, n1, n2, and n3, and sigma plus, sigma minus. And so for another spatial point, we are going to have different variables, m and pi, say like that. And so we can write down the Einstein equations for this kind of thing. Now this, of course, if you in the general in homogeneous case, of course, you have PDEs or an infinite dimensional dynamical system that describes the Einstein flow in this case, but each point, spatial point, from those equations, the PDEs, satisfies this kind of system, which is of course identical to the homogeneous case. But in this case, if you go to a different mixmaster point in the inhomogeneous case, you have of course this system, but in a different set of variables. So these are the evolution equations. This is the constraint. And Q here is given by this. The S plus and the S minus are these functions here dependent only on the n variables. And similarly for the mixmaster point B, so it will have identical equations to those, but in terms of the m and the pi variables, like that. So P here is the equivalent of Q, but in the pi variables. And so these are the shear equations for the mixmaster point B. And what I have done is that I have followed the previous synchronization technique and put n equal m for the first three equations. Okay, so now I have a system that has equations for the mixmaster point A and another set of equations for the mixmaster point B. And the basic problem now becomes the following. In this kind of inhomogeneous mixmaster setup, is it possible for different mixmaster spatial points, say A and B here, to synchronize in the sense discussed previously towards the initial singularity? And if yes, what are the implications for the whole picture? Now, this is the basic question, and this is the unexpected, I should say, answer that indeed, yes, it is possible for to have a synchronization in cosmology. And then, as I will try to explain, the implications of this kind of thing are really very, very interesting. Okay, let me show you how these things may arise. Okay, now we have these two mixmaster spatial points A and B, like that, and we think of them as a transmitter and receiver pair, like we did before, as I showed you. And suppose that A is in the past null cone of B, so it can send actually a light signal. A can send a light signal to B, and so suppose that A sends a light signal containing only part of the information that A carries. That is, suppose that it contains only the n variables, the signal, and that signal is received and adopted by B. So in that case, in this sense, we set the m variables of the B variables m equal to the n variables of A, and we have this system here, which is the equations that are satisfied by the point B, and also there are these equations for sigma plus and sigma minus that are satisfied by the point A. So in this case, we are led to consider a transmitter-receiver cosmological system for the 2 points A and B, like that. Now, okay, so what we have done and have from now on is to introduce, like before, like in the general sync dynamical system method, we introduce a cosmological sync function omega, which in this case is the difference of the remaining variables. So omega is sigma minus pi, like that. And we say that the 2 points will synchronize provided that A goes to 0. As tau is the dynamical, the dimensionless time that according to this, so if T is the proper time, tau is satisfies dt over d tau equal 1 over h. H is the Hubble expansion in the inhomogeneous case. So the singularity is at minus infinity. So we say that we have synchronization between the points A and B, provided that omega asymptotes to 0, like that. Otherwise, we say that A cannot synchronize and evolve independently. Now, there are different kinds of synchronization in the literature. Basically, there are three kinds of synchronization: complete, phase synchronization, and the last one is generalized synchronization. All three kinds are in principle possible in inhomogeneous cosmology. And I will show you, I've written here the first general result that we have proven in the paper, which says the following thing. In the following cases, we have complete or phase synchronization between two arbitrary mixmaster spatial points A and B, with A in the past of B. So these are the cases where we have zero coupling and P equal Q, linear coupling or general coupling, like that, between A and B. And also there is another last case that was done by John Barrow last year actually, which is called the Kuramoto coupling. This is a phase synchronization problem, but I will not say many things about this. Actually, we have also analyzed this case, this last case, in this kind of method that we have here, and of course we find that the 2 points are able to synchronize also like this. Okay, now of course I don't have the time to give you proofs of this, but I can also just to give you a taste of what it is for these things to synchronize. Let me give you a sketch of proof for the simplest possible case, which is the zero coupling case with P equal Q. So this is the transmitter receiver system. In this case, there is no coupling, and so we have the point A, which sends the signal. These are the shear variables sigma, and the point B has shear variables pi, and so this is the system. Now, if you define the omega sync function like this, then you have this system for the synchronization function, and you can show very easily that this system admits a Lyapunov function that is a positive function that has a negative derivative like this, and at 0 is 0. Okay, so this is very easily you can see this very easily by just working a little bit with these two equations, so that the system has a Lyapunov function, which actually means that the state omega equals 0 is globally asymptotically stable. Okay, in fact, you can show something more, that the state 0 is approached exponentially fast because of this. If you take this equation and work a bit and solve, then you can have this kind of thing. So actually, this shows that in this simplest of all cases, the 2 points synchronize completely and stably, and also one synchronizes to the other exponentially fast. Okay, now this is the first result, and the second result, which I'm just going to mention, is that once the two that we have shown is that if we have these two synchronized mixmaster points A and B, then these have the following property, namely that they evolve oscillating in perfect harmony, unison, towards the singularity, in the sense that the Kastner exponents of the point A tend to those of the point B, like that, which basically means that both of these sets of Kastner exponents can be parametrized by the same U. In other words, in the paper we show that actually the U BKL map U for all cases, I don't have time to explain here, but also the BKL maps tend to each other, provided that we have synchronization between these 2 points. Now, this actually is a very, very interesting result, because it says that this is the summary of what I've just said. Every space-time point is constantly sending and receiving signals from other causally connected space-time points, and these spatial points shift and adjust their states of oscillation constantly, resetting them. Resetting means that the U BKL map resets. Okay, so actually they oscillate chaotically, but with the same, exactly the same U maps. So this is the important part here, that the homogeneous mixmaster situation actually is described by resettable oscillators, something that of course cannot happen in the homogeneous mixmaster case. And so sync organizes the 2 points or the regions like that to evolve towards the past singularity in perfect harmony. Now, of course, no such situation is possible in the homogeneous mixmaster. Now, in the few minutes that I'm left, let me give you some implications of this well, unexpected result here. Now, the first one has to do with the entropy problem. Now, you see what happens. So consider that the following situation. Suppose that we move towards the singularity, the past initial singularity in the BKL sense. And here we see some time slices. So T1 is a time later than the time T naught. And these dots here or stars mean that as we go towards the singularity, more and more points get synchronized with each other. Okay? Now, in such a situation, it's not difficult to see that the entropy of the universe as we go towards the singularity is actually reduced, is decreasing. And this is because more and more information is lost because more and more states are synchronized. So in fact, it means that as a result of sync, entropy reduces more and more, and at the states at the end where we have complete synchronization, then the entropy tends to zero. So in fact, this result means that the initial state is actually the simplest possible state, a state of minimum entropy. So because of sync, we have a universe that has a very simple initial state with a state of minimum entropy as we go towards the singularity like this. Now, this is actually the next one is my last transparency here. So let me just say something in the few minutes, 2 or 3 minutes, about the horizon problem. Now, perhaps you know what the horizon problem is. Well, this is I've made here a sketch of the horizon problem. Now, suppose that we have the horizon problem is this. Suppose that this point here, you may think that is a point like now or during just after the Planck time. It doesn't really matter. So suppose that we have the points A and B like before, and A sends a signal to B like that. What we have shown is that if A and B are like that and A sends a light signal to B, then A synchronizes with B. So in fact, the same happens with C here, synchronizes with B. And so this whole area here of spatial points actually synchronizes with B. The same happens here with these points here, and all these red points synchronize with E. But of course, B and E have not have the time to communicate with each other. They are causally disconnected. These red regions are causally disconnected. And so if we are here and look at all these causally disconnected regions, we wonder, for instance, now, because of the existence of horizons, how it can be that causally disconnected regions, say, for now, we have all the regions in the sky that are more than 15 degrees apart. They are completely synchronized, so to speak, or similar, and we don't know why. Now, of course, here we know why, and there's an explanation, because if you take any point here between A and C and another point there, then this point will synchronize with B, and B sending a signal to G will synchronize with G, and so this point here will synchronize with G, and similarly here will synchronize with G. So these two areas here will be synchronized with each other, even though they are not in causal contact. They were never in causal contact. However, they are completely synchronized. Okay, so I think this is a solution to the horizon problem. And in fact, I think that the horizon problem in cosmology represents the biggest example of sync ever, you know? So this I think is a very dramatic implication of the idea of sync in cosmology. Now you can, if you are interested about sync, I strongly advise you to listen to the TED talk of Steven Strogatz, who is an expert in sync. This is quite an amazing talk, actually. In YouTube, you can find it here. He talks about fireflies, birds, and fish, and everything that can synchronize. Very, very serious stuff. Thank you very much. Okay, this is the end of my talk. Do you have any questions, or you want to ask something, or you have any comment? Okay. If you don't have any comment, then or question, then we can continue with the talk of the next talk. Now the next speaker is Philippe Leflot. Hi, Philippe.
Hello.
And he's going to talk about the scattering laws of bouncing universes. Okay, I think you are here. I will just stop sharing my talk, and you are on. I will just stop my video and mute myself. So thank you very much.
Okay. Let me see. So I need to work out the sharing part. Is this correct, like that? I suppose so.
Yes,
right?
yes, perfect. We can hear you and see the slides and everything. Thank you so much.
Okay. So I'm really very glad to be speaking in this session, and I want to thank you, Spiros, for the invitation. I'm going to present a work that is joint with Bruno Lefloc in Paris and Gabriele Veneziano at CERN. And first of all, what I should do is I should present myself in some way by saying that I'm a mathematician, and I'm interested in matter fields and the global dynamics of matter fields. I was working in non-relativistic fluids before, mathematical aspects of it. And in the past 15 years, I started looking at general relativity. And so the way I see these sort of questions is to include gravitational waves together with shock waves, or possibly phase transition interfaces. So this is the way that I proceed. And the techniques I've been using comes from Lorentzian geometry, partial differential equations, and of course, understanding the physical modeling behind. Having weak solutions to fluid equations or to the ancient equations is a very, very interesting subject that is mostly open, but these are the questions I've been looking at. So for today, I would like to show you this work with Bruno Lefloc and Gabriele Veneziano, where we try to propose a new perspective on bouncing cosmologies. So we have in mind the usual setup of a contracting and an expanding spacetime, and we are interested in not only going to the singularity, but actually crossing the singularity by imposing certain bouncing junction conditions. So all the game is to understand what are the rules to pass from the contracting region to the expanding region. So we move toward the singularity. This is the direction we consider. Of course, this subject is very old, and there is a very large literature. I put a few names on the screen. And so we built on what all these people have already understood. And the point of view here is essentially mathematical, and it has to do with the question of, can we classify? The basic question is whether we can classify all possible junctions. So we are not interested at first with a specific model of extended gravity. But we want to take the point of view that even if you don't know which model you should introduce from the physical point of view, you can ask what are all the possible junctions that could arise from any kind of model. So that's basically the question we have answered in this work, and I will try to tell you what we have found, which I think is quite interesting. All this work is done in the regime of quiescent cosmology, where certain monotonicity properties are satisfied. So we are not in the general BKL regime where there would be oscillations, but we look at a monotone situation, which is the case for instance, if you have certain symmetries in your system, or some matter model, or high dimension. This is a typical regime that arises. So what we do is we do a classification of all bouncing laws near a singularity hypersurface. We view the phenomena as a kind of scattering, and we formulate the junctions in a way where we can separate junctions that we call universal, and junctions or junction conditions. I mean, there is one junction, but in these junctions there are different rules that you have to apply, and some part of it is universal and some part of it is model dependent. And we also have been able to use this construction to build cyclic spacetimes when two gravitational waves collide and we go beyond singularities. And there are possibly many, infinitely many, or finitely many singularities in the construction. Of course, this is done under symmetry, this last construction in T2 symmetry. That's what we can do also to do the global evolution problem. Now, here I'm really asking today a very local question: how you pass through the singularity by using scattering maps, how you define a notion of cyclic spacetimes, covering the contraction and the expansion part of the spacetime, and most importantly, the classification of all scattering maps. So this is the main result I want to show you, is this result of classification that we have found. So let me start by formulating a framework which start with this question of looking at general bouncing cosmology and looking for classes of physically meaningful and mathematically meaningful conditions, junction conditions, of course, going beyond the Israel junction conditions. So if you think of singularities in gravitational singular or impulsive gravitational waves propagating, of course, you think immediately to the work of Israel, but this work and the junction conditions that he defined only apply to regularity hypersurfaces, meaning that you approach the hypersurface, all quantities have a finite limit, and then you may jump on another region of the space-time, so there is a discontinuity of some of the quantities, but all the quantities have some limit on each side of the singularity. Of course, this is not the case if you talk about bouncing cosmology. And in addition, you also know that there is a very complex dynamics that can happen, as we just saw in a talk of Spiros. So that's not the regime I want to talk, at least not immediately. I want now to consider the regime where you have a certain monotone behavior. You have a specific Kastner exponents when you reach the singularity, and now you want to jump typically certain Kastner exponent before and to some other Kastner exponents after the singularities. That's typically the situation. So let me introduce some notations. I'm going to denote certain singularity data, either the past or the future, by this notation. So G will be the rescaled metric. I will tell you exactly what I mean by that, but there's a certain rescaling because there is a blow up, so you have to do some rescaling to produce some finite objects. And I will denote that G plus minus on both sides, and there's an extensive curvature, and you have two data for the scalar field. What I'm presenting is a situation where you have a scalar field denoted by phi. So phi 0, phi 1 correspond to the 2 degrees of freedom of the scalar field. And after rescaling, these quantities are finite on the singularity, in a way I explain in a minute. And so what we mean by a singularity scattering map is a map that takes this rescaled data on one side and produce rescaled data on the other side of the bouncing. Based on that, we are going to define, of course, a cyclic spacetime, because you can repeat the process as many times. So in the end of the day, what we are going to define is a notion of spacetime that depends on the choice of the singularity scattering map. Okay, so I'm not telling you directly how the bouncing should be done. I'm looking for a classification of all possible bouncing rules and to parameterize them through a certain scattering map. Okay, so this is a goal. Of course, in a last stage of this program, we want to identify this map. And that's basically what all the people I mentioned on previous slide have done to figure out what are the junctions. Okay, but somehow we proceed in a different way, which I think is quite interesting. So the way we produce the classification is to work with general spacetimes, not on spacetime with symmetry, not looking at spatial junctions. And to achieve our classification, we need to rely, that's basically the only things that we have are the constraint equations, but which we have to write in some asymptotic form. So this is what is left from the usual Einstein's constraints on a regular space-like hypersurface. So what is left when you approach the singularity, then you have certain constraints, asymptotic constraints, that relate precisely the data that I wrote upstairs on the screen. And so I already told you that some of that will be universal or model dependent. So you are going to see that in a few minutes. So first issue is how we rescale our metric in order to produce some finite limits. So this is done in a rather natural way that basically goes back to BKL, where we introduce a Gaussian foliation by space-like hypersurfaces. We express the Einstein equations in the usual ADM form. So you have this system where, as usual, Rij is a Ricci curvature, and you have a term Mij, which represents the matter content of your spacetime, which in my case will be a scalar field. You also supplement this with a constraint Einstein equations, and there is a wave equation, or it could be a Klein-Gordon equation if you include a potential. That's not important for what I'm going to describe. So you have a certain wave or Klein-Gordon equation for the scalar field. Mathematically, this model is known as the Einstein flow and is studied for regular solutions by a number of people. What I'm going to do here, I'm going to look at singular solutions that blow up on a certain singularity hypersurface, as you expect. So this is my picture. In the past, you have a flow, G star, K star, phi star, that depends on tau. So tau is my time variable. And these quantities are defined on a hypersurface, on a three manifold, and they evolve to the singularity. And again, there will be some jump, and you continue the flow on the other side of this hypersurface. Now, what do we mean by G minus, K minus, phi 0 minus, phi 1 minus? We simply mean what we could guess by looking at a class of spatial solutions, which are the Kastner profiles given by this usual formula. So you take these solutions, and of course, you know that if you want to extract some finite limit, you should look at the Kastner exponents, you should look at certain coefficients in the expansion of the matter field, which on the screen are called phi 0 minus, phi 1 minus. And the second fundamental form, if you write it in a suitable frame, will be diagonal, and again, you can extract the Kastner exponent. So basically, you base your intuition on the typical solutions that you know near the singularity, and based on that, and of course, based also on the ansatz, BKL ansatz that we know, you realize that you know that the ODE and ODE model should be relevant near the singularity. Okay, so this is what is behind. There's an ODE model. This ODE model can be solved basically explicitly, and it depends on certain parameters, and the parameters are precisely what I call G minus, K minus, and phi minus for the matter field. Okay, so what I'm going to do, I want to construct local solutions. So I do that by using the so-called Fuchsian method that you probably all know for ODEs, but here we will need to apply it to partial differential equations for the Einstein equations. But we solve, so we solve from the hypersurface, the singularity hypersurface, towards the past, we solve towards the future, we get local solutions defined, and they are found by writing an asymptotic ODE system, again, based on the BKL or the so-called velocity-dominated ansatz. We essentially have to remove all spatial dependency, but this is a little bit more tricky than that, but the essential idea is to do that. And then we solve Fuchsian, we have singular ODE or singular PDE for solving the Einstein equations that we have to address. And this sort of techniques has been first developed by Alan Rendell in the context of the Einstein equations maybe already 30 years ago, maybe. So our main issue for us is how we cross the singularity hypersurface and how we glue together a Fuchsian type solution in the past to a Fuchsian type solution in the future. How do we do this gluing? So as I said before, we need to study the asymptotic data and understand, describe them somehow through the Einstein constraint equation. Okay, so let me try to formalize this a little bit. So we have a definition saying that a past singularity initial data set for us will be a metric and an expansive curvature and two matter field. The Riemannian metric has no restriction. The tensor K minus has trace equals 1. So this comes from the CMC assumption that we put on our slicing. And then we have two constraints, the Hamiltonian and the momentum constraints. The first one is purely algebraic, because it's the asymptotic formulation of it. So it has to be simpler in some sense. So some of the terms have been neglected. And the momentum constraint has a form that I wrote in the last line. And this suggests to introduce a space of all singularity data. So this is a space of data, of singularity data, or you could call it initial data if you wish. This is the data that you put on the singularity if you want to solve and construct your spacetime by solving an initial value problem, but from the singularity. Okay, so this data, these equations are a little bit tricky to study. They are not like the usual constraint equations. Now, based on this data, I can now construct what I call an asymptotic profile, or it's called ancient geometric flow, if you like. So it's a flow on your slice, on a manifold, that is defined explicitly by simply rescaling by 1/2 k minus to define k star. Then the metric is a little bit more complicated because there is some exponential metrics tau to t 2k minus that comes in front of the metric. And the matter field is defined by log of tau plus a term independent of tau. And so this is the ansatz that you put in your Einstein equations in order to construct a solution. Okay. Again, I'm basically repeating what the BKL ansatz is telling you to do, but I need that in order to proceed for the results I need to present. I want to present. The regime of interest of the so-called quiescent singularities is characterized by the fact that K minus is positive. And you will see that this condition will come a couple of times. So based on this setup, I'm now in a position to define what we mean by a scattering map. So it's a map that takes data in our set of asymptotic data and produce another asymptotic data. Okay, it's just a simple map But of course, it's a map acting on functions that are defined on a hypersurface, on the singularity hypersurface. First of all, it has to be diffeomorphism in covariance, so there is a condition of being coordinate invariant, so otherwise it would not be realistic at all. And then essentially there is only one assumption that we put in our theory, which is, we call it locality property. In fact, it's going to become to be ultra locality property in a few seconds, in a minute. But we start with this idea that locality property simply says that your junction map can involve derivatives of the data before. So you go from the data before to the data after the bouncing, and locally in a pointwise way, you can look for formulas that might involve possibly many derivatives at a point, but it's local in some sense, right? So you're not allowed to use a global conformal factor or something like that. But okay, so I mean, this is I think very reasonable assumption physically. And then based on that, so this is our only notion for assumption for the static map. And then we produce now a notion of cyclic spacetime, a definition of cyclic spacetime, by saying that if you give me a Lorentzian metric, what I'm going to assume is that it is regular by parts. There is a regularity domain where I'm able to write the Einstein equations in a classical sense. Then I have hypersurfaces of singularities, and at every point in a neighborhood of this singularity locus, I'm assuming that there exists a local Gaussian foliation. And I introduce similar notations as we had on the previous slide. And I can, based on that, I can impose a junction condition, which consists of taking my solution to the Einstein equations and rescaling it in a way that is consistent with the BKL ansatz, getting some finite limit, and imposing the conditions that the finite limit on one side are mapped to the finite limit on the other side through the scattering map that I have chosen. Okay, so all of that is very natural. And to maybe let me go quickly through this slide. And this slide is simply telling you that we can produce a local theory solving using Fuchsian techniques. We solve in one domain, in the other domain, and we glue according to our junction conditions based on such a map. And maybe the only idea I was going to miss is that we impose that our scattering map preserve this quiescent property. Okay, so if K minus is positive on one side, it has to be positive on the other side. And all the examples we have looked at are consistent with all the assumptions I will show you today. Okay, so now I'm moving to maybe the most interesting part for this audience, which is a classification of scattering maps. And the locality property means what I repeated on the beginning of the screen, that S, so S of the data depends upon our data and possibly derivatives at the point X where we are looking at these quantities. And so the only assumption that we put is the one I'm showing you now, is that we assume that our map is ultra local, meaning that it does not involve derivatives. And again, at least I would say most of the examples we have looked at seems to be very consistent with that. But of course, it's yeah, I mean, it's difficult to actually prove things like that, starting from the full model and a full model of modified gravity. You need to assume symmetry, etc. That's not what we do here. We start from somehow the top or a different position, and we try to produce all possible maps. So ultra local properties, this is the only assumption. And then we have still the interest of having a full classification. So then we introduce some additional conditions that will only help us in producing a classification. So we introduce the idea of conformal map. If you simply need a conformal factor to go from one side to the other side of the singularity, or rigidly conformal map, it's a variant of that. Momentum preserving, K minus equals K, K plus, momentum reversing, idempotent, If when you iterate the map, you go back to the identity. We do also time-like hypersurfaces. And of course, these issues of idempotent or invertibility that comes especially for time-like singularities. So we have all these conditions, but these are not conditions we necessarily impose. These are just conditions that we have looked at as examples, if you like, at subclasses of our general classification. So our strategy are already outlined it by saying that we will play with the constraints. We construct a class of general solution without symmetry. And by using that, we can probe the properties of the scattering maps. And by doing that, we discover that there are actually very few degrees of freedom, which we parameterize by a few functions. So this is basically the message that when you cross a singularity, you cannot cross a singularity in a very general arbitrary way. There are actually one or two functions that characterize the important dynamics to jump from one side to the other one. We have a classification that starts with a simpler class of rigidly conformal maps, and then we do the general class of ultra-local maps. And now I'm getting to it. I show you the result for rigidly conformal maps in two parts. So we discover that there is a class which we call isotropic rigidly conformal, where the metric is simply, so G minus, is simply rescaled by a conformal factor that depends on the matter content before the singularity and the determinant of K minus. There is a constant phi. So you can see, for instance, that the matter field is completely erased. K plus goes to trivial delta over 3. So this is maybe the less interesting situation. But I guess it could happen. And then we have a non-isotropic rigidly conformal bounce, where now we have basically one parameter to describe this bounce, which is a scalar function f. So it's a function of one scalar variable. And from this f, small f, we construct a big F by simply some integration. Phi has a dimension of the matter field. We also construct a mu that is also certain combination of our function f. And based on that, we generate the conformal factor, we generate the form of the matter field, we also generate an explicit form for K plus. So everything is explicit, only depends on one function of one variable. I mean, and we put really almost nothing here, rigidly conformal, ultra-local. This is our assumption. Now, if we remove rigidly conformal, the formula are slightly more complicated to write, but the philosophy is exactly the same. Okay, so lambda becomes now, instead of a scalar function, it will be a two tensor, but it's the same idea. And the phi that comes, there is a capital phi that comes in the second classification. It has to do with the canonical transformation. Now, having these formulas, we thought about it, and we figure out that in fact our result can be stated in terms of three laws that we call the three universal laws of quiescent bouncing cosmology. So the first one has to do with the Kastner exponents. So they jump, but they jump in a very simple way. There is just one scalar gamma that tells you how you go from the Kastner exponent one side to the other side. Then the second law is the way that the matter transform. So you could see on the previous slide in the simplest case that there was a simple one function of one variable. So more generally, it's described by a nonlinear map that lives in a phase space. And this map has very nice geometric property to preserve the volume form and to only depend on this scalar invariant. And our third property is basically the formula I show you that were a little bit complicated on the previous slide. They actually take this very neat form where the metric after the bounce is a certain exponential of sigma 0, sigma 1k, sigma 2k square. So where you need to I need to tell you what sigma 0, sigma 1, sigma 2 are, but there are anything in the isotropic bonds, and for non-isotropic bonds, they are given explicitly in terms of phi and gamma, exactly what I told you before, but it goes through, it can be formulated through three laws like that. So I guess I'm almost finished. So let me say that, of course, there is a very large literature that I need to read myself, because my co-authors are theoretical physicists, and they know a lot about this field, and myself, as I said in the beginning, I'm a mathematician. So what I want to do is really look at specific models and understand what are the properties of the quadratic maps that people have understood before. So what we believe with my collaborators is that the classifications that we have uncovered here, having a complete classification where we can make different subclasses of being conformal, non-conformal, we treat space-like null, time-like hypersurfaces, we treat various matter models. So we believe that our classification is going to be useful, especially formulated as laws, certain laws where the universal aspect is understood and model dependency is put forward. So we believe that this is useful as a guide to uncover the relevant structures for various microscopic corrections. Our classification does not regard the specific regularizations somehow, but of course they are important, but we can now input this in our classification. So I'm going to stop here. So, sorry, maybe I speak a little bit too much. There are 3 papers that we have in collaboration, and I have also 3 other papers with only with Bruno Lefloc that you may want to read. The first 3 are more maybe physical, and the last 3 are more written in a mathematical style. So thank you very much, and thank you again for the opportunity to speak here.
Okay, thank you very much, Philippe, for your very interesting talk. Are there any questions? If not, I have just one question, you may call it. Now, this is very interesting, this classification, the conformal case, etc. My question is this. If you take, apparently, for some cases, as you say, you can jump through, the other side, right? To put it somewhat informally, what you do.
Yes.
Now, in that case, have you considered the behavior of geodesics? Apparently, the geodesics in some cases will not see the singularity, right?
Yeah. I mean, we no, geodesics, we didn't look at it very carefully. We look at questions about volume and
yes,
temperature. So I mean, like the basic things, but we didn't look so much at the geometry, the local geometry.
I think, Philippe, I think probably that the behavior of geodesics in your classification will actually enhance what you try to do, because they will, if you have some jump discontinuity, maybe this will show in the geodesics, or if you have nothing, then it will just pass through. Like in some very simple examples, of sudden singularities, I'm sure that most of the types of singularities that we have fall into your new classification, which is actually very interesting, I think.
Okay. We look at it and maybe talk later.
Very good. Yes, of course. Thank you so much. Okay. Thank you again. Okay, our next speaker is now Iphigenia. 1 second to find the program. So okay, our next speaker is Iphigenia Claudatou. The title of her talk is Brain Wall Singularities in a Fluid Bulk. Okay, Iphigenia, are you here?
Okay, yes, I'm opening the camera and I will try to share this presentation. So let me just move the window and make it full screen. Okay, can you see?
Yes, yes.
It looks fine. Okay, so let me put up. Okay, hello everyone. Thanks for having me in this meeting. It's a pleasure to discuss with you all these nice topics. My talk today is about singularities that we meet in brain worlds. This is joint work with professors Ignatios Antoniadis and Spiros Kotsakis. The outline of my talk is the following. I'm going to give you first a discussion, a background on the class of brain worlds that we use in our study, and state the open questions that motivate our work. Next, I'm going to give you the setup of the brain world, that is the field equations that govern the dynamics of the model. I'm going to study two types of bulk matter. First one follows a linear equation of state. So pressure equals gamma constant times the density. And the second type of matter is a nonlinear fluid. So it follows an equation with a new exponent now on the density, which is denoted by lambda. The study of this second type of matter can be divided into two major cases. First case is that of lambda less than 1. We're going to see that these solutions exhibit finite distance singularities. And the second case is that of lambda greater than 1. For this case, we find regular solutions, and we're going to construct a matching solution which successfully localize gravity on the brain. And last thing, I'm going to conclude and also give you some bibliography. Sorry. So the idea behind brain worlds is that we live in a higher dimensional space-time, and that the observable universe is modeled by a brain, a hypersurface that is located at an arbitrary but fixed position along the extra dimension. In our class, we use 5 dimensions in total. In the framework of such models, we can re-examine challenging problems of classical cosmology. For example, the cosmological constant problem, which is basically the disagreement between theoretical predictions of on the value of the cosmological constant and the observable ones. A new approach to such a problem was done by Arkani, Hamid, Dimopoulos, Caloper, and Sudrum in a paper called The Small Cosmological Constant from a Large Extra Dimension. And their model consisted of a 3-brane flat one that was embedded in a 5-dimensional bulk. The bulk was filled with a massless scalar field. And the interesting aspect of this model is that the energy spills from the brain into the extra dimension and gives, in this way, 4D gravity macroscopically with a vanishing cosmological constant. A main feature is that it exhibits a finite distance singularity. And we wish to further examine the nature of this singularity and if it is generic in a way. So the open questions from our point of view is this finite distance singularity generic? Is it possible to avoid it, and what are the appropriate conditions that make this possible? So we generalize the model by substituting the scalar field with an analog of a perfect fluid. So the massless scalar field can be thought of as a fluid having a gamma equals 1. Now this equation of state, we let gamma be arbitrary, and we want to see what happens to the singularity. A second way to generalize it is by substituting the scalar field with a nonlinear equation of state. The reason for shifting from this one to this more complicated equation of state is because the first one doesn't give us the desirable properties, let's say, that we want. And I'm going to show you what I mean in a little bit. Now, we have generalized this model by other ways, for example, by considering a curved brane instead of a flat one, or considering mixtures in the bulk that interact. I will give you the bibliography in the end, and if you're more interested in such cases, you can have a look. So the setup of the brane world is the following. We have 5 dimensions in total. The extra dimension is y, it's the 5th dimension. The G4 refers to the brane, so we have a 4D flat brane and flat metric, sorry, for the brane. A of y here is the warp factor, and the energy momentum tensor that we consider takes this form over here. So we assume that there is a fluid that has a density rho and pressure P. And this density and pressure are functions only of the 5th dimension y. The velocity goes along the 5th dimension, and wherever you see capital letters, they run from 1 to 5, whereas small case letters or Greek letters run from 1 to 4. We can derive for that Assange the Einstein equations for the metric and energy momentum tensor that we have. And we end up in these 2 equations. And also we have the conservation of the energy momentum, which is described by equation 5. So to solve the system and see if there are finite distance singularities, we take equation 5, okay, we do a standard procedure, just integrate it and find rho in terms of A. We end up in this expression over here. Then we can take this rho and put it back, of course, in the first equation and get A in terms of y. If we do that, we find equation 6. And once we have A, of course, then we can find rho in terms of y. From the solution, what we see straightforwardly is that there is a finite distance singularity. So if you let y take the value plus minus C2 over this factor over here, you will end up with the bracket here being 0. And then a singular behavior of A will follow. And the nature of that behavior depends on the sign of this exponent, whether it is positive or negative. On the other hand, rho, again, when the bracket becomes 0, will diverge because of the negative exponent. And so we do face this finite distance singularity in this case with a linear perfect fluid. The behaviors are depend on gamma. So for gamma greater than -1, that exponent that I told you about is positive, so A will go to 0, rho will diverge. And for y less than -1, A will diverge and rho will diverge as well. Now, a way around the singularity is to try to do the following. Since we want to introduce the brane at, and you can place it at y equals 0. Once you introduce the brane, then you have a y minus y symmetry, which is described by the existence of the absolute value here. Then you can choose appropriately your parameters. For example, if you look for solutions gamma with gamma greater than -1, you can choose C2 greater or equal to 0, and choose the plus sign for y greater than 0, minus sign for y less than 0. In this way, the plus minus that we had over here gets absorbed in the absolute value. And now the thing that happens is that the bracket can never become 0 because the absolute value of y can never take the value minus C2 over this factor because minus C2 is negative. In a similar way, you can write rho, of course, and you see that rho will not diverge with this choice of parameters. On the other hand, if you look for solutions for gamma less than -1, you can choose C2 less or equal to 0 and make the opposite choice for the plus and minus solutions that we did before. And as you see, when the absolute value of y, again, can never take the value C2 over this factor because C2 now is negative. So we escape the singular behavior for A and rho in a similar way. Now, once we introduce the brane, we have to make sure A remains continuous and rho remains continuous. Also, we have to take into account the jump of the extrinsic curvature. So as I said, the brain divides the bulk into the space-time, the 5-dimensional space-time, into 2 regions. And what I have written over here with K alpha beta plus is the value of the extrinsic curvature for, let's say, y greater than 0 on one side, and K alpha beta minus is the value of the extrinsic curvature on the for y less than 0. This jump is related to this expression over here that involves S alpha beta. S alpha beta is acts like surface energy momentum tensor. It describes the fields that live on the brain and vanish off the brain. And they are connected with F of rho, which is the brain tension, the notation for the brain tension. So if you take into account all this, and for example, focus on solutions for gamma less than -1, the first case, I think, the second case we had, then you see that the arbitrary constants appearing in the solutions are connected in this way. C1 plus is equal to C1 minus, C2 plus equal to C2 minus, and also you get an expression for the brain tension. Again, C1 plus, C1 minus are the values of the arbitrary constant C1 for y greater than 0 and y less than 0. Now, once we introduce the brain, we want to also check physical constraints. For example, we want to check the energy conditions, and we want to check the possibility of localizing gravity on the brain. To formulate the energy conditions, if you recall, the energy momentum tensor was static with respect to t. Then what you can do is you can say that the fluid can be reviewed as an anisotropic one with an energy momentum tensor of this form. So there's a different pressure along different directions. Okay, this is along the along different dimensions. So this is along the y direction, and you can figure out also the values on the other dimensions. And once you make them equal with the previous energy momentum tensor, you can derive the expressions for rho naught here, p naught, in terms of rho and p that we had before. Then you can apply the energy conditions on this energy momentum tensor and translate them back in terms of p and rho. What we find here is, for example, the weak energy condition results in having p, the pressure greater or equal to 0, which in turn translates, because p equals gamma rho and rho is positive, to gamma being greater or equal to 0. The strong energy condition, on the other hand, will give you 2 possibilities. Either the pressure is negative and y is between -1 and 0, or the pressure is positive and y is between 0 and 1. Now, in any case, you have to have at least gamma greater than -1. So if you look over here, we had either gamma positive and gamma at least greater than -1. Now, the localization of gravity, for the localization of gravity, we want to make sure that the 4-dimensional Planck mass is finite. And this is monitored, let's say, by this integral of a squared between -yc and yc, as yc goes to infinity. So this integral has to remain finite. And if we plug in the a squared for our case, then we see that the localization condition translates to having gamma between -2 and -1. So we see that they don't match up, the conditions. This is a summary of the case of a linear fluid. We see that there is a finite distance singularity, which can be avoided by exploiting the symmetry that the brain introduces. But the matching solution that we get in this way cannot at the same time satisfy energy conditions and the requirement of localizing gravity in the brain. So you have to make a compromise between the two. That is actually the motivation to look for a more appropriate, let's say, equation of state. Now, this type of equations of state have been used in classical cosmology. with promising results in the sense that they have managed to escape the big rip singularity at late times dynamics. So we hope it will do something similar to our class of models. Now, if you input this new equation of state in the energy conditions, and we have also included here the null energy condition, then you see that there is a common inequality to be satisfied by all conditions, which is this one, and it basically says that P plus rho is greater or equal to 0. So we want to incorporate this a priori, let's say, in our solution. To do that, we do the following. As you remember, we have to use the continuity equation and integrate to get rho in terms of A. While we integrate, it appears there appears a logarithmic term that has this argument over here. So we would normally put an absolute value, but we just ignore it, and in this way, our solution has this restriction from the beginning. And we end up with this expression for rho. C1 is an arbitrary constant that is positive. Okay, it is related to the original, let's say, arbitrary constant, and we have renamed it C1. Now, because of this particular equation of state, there is something happening in the density. If you notice, if A to this power takes the value gamma over C1, rho will collapse here. And if you have lambda greater than 1, that means that rho is going to become divergent. So in order to escape such a singularity, we're going to focus only on values of gamma that are negative. So we take this expression we found for rho and put it in the analog of the Friedman equation. I think it was the first field equation. And we integrate. So when we reach this function, this integrand function, we see that it is no longer straightforward to integrate. The only case that the integral is computed directly is when this exponent over here becomes a negative integer. I'm going to talk about this case in a few slides later. For the time being, let's say this doesn't become a negative integer, so we have to actually take it as it is and figure out the solution, let's say, for lambda less than 1. What you can do for this integral is that you can express it in terms of the hypergeometric function. For those who are not acquainted with the hypergeometric function, it is defined by this series expansion over here. It converges in a disk with radius 1. And it has also an integral representation, which is actually what we use ourselves here, provided this condition is true. So we want to have B less than C and both of them positive. If you have a look back in this hypergeometric series, then because lambda is less than 1, the parameter B is indeed positive and C is B plus 1, so it is bigger than B. So everything, we have checked that everything is valid for the integral representation. And we can now start looking for the asymptotic behaviors of this solution that is given in such an implicit form. The singular behaviors that we're interested in is that that of A approaching 0. So if A approaches 0, the exponent of the argument here in the hypergeometric function is positive, which means that the argument is going to approach 0. If you look over here, the series starts with 1 plus, and then it has ascending powers of Z. So if Z goes to 0, then the hypergeometric function will go to 1. But because of A squared here, you will have that the whole right-hand side will become 0. And that means that Y now can take the finite value. So it is again singular, the solution. As Y goes to plus or minus C2, you have a finite distance singularity with A approaching 0. You can do the matching that we did before, and you can also try to figure out if localization works, but the problem is that the localization of gravity doesn't work even here. It persists, so we have to, I will skip the matching for this one and move to the more interesting case, which is for lambda greater than 1. Now, so for lambda greater than 1, we have two major cases. This is the easy one. When lambda takes the values 2k plus 1 over 2k, the exponent we had before that I showed you here on the integral, this exponent becomes negative. And that means that you can directly go and integrate. So the simplest case of all is the one you get for k equal 1. And this means that lambda is 3 over 2. This is a nice example because it has evident properties that we can see straightforwardly. And the nice thing also is that whatever properties it has, they get inherited in the solutions for general lambda. So I'm going to focus on these and use it as a guide to show you the behavior of the solutions. So once you put 3 over 2 in here, the exponent becomes -1. Then you can integrate and you get this solution over here in implicit form. Checking for singular behaviors, if we let A approach 0, first term collapses, but the logarithmic term here will make the whole right-hand side approach infinity, which means that Y now will approach plus or minus infinity. And this means that the singularity we met previously shifts now at infinite distance, which is good news. Also, if you let A approach infinity, all this will diverge, leading to Y going to plus or minus infinity. And I have also written the assorted behaviors of P and rho for the behaviors of A. Now, even if the solution is regular, we still have to introduce the brane. And the reason is that in this way, we can localize gravity. So we go ahead and just write the solutions. This is the Y plus, just means the plus branch, the positive branch, the solution we get with the plus choice in the previous expression over here. And Y minus is the solution we get with the minus sign. And I have renamed the arbitrary constants so that they look homogeneous here. So C2 plus is just the arbitrary constant on the plus branch, and C2 minus refers to the minus branch. Now we want to see a little bit the behavior of them and see how we can match them. So we need to check out the derivatives. Checking the first derivative of the plus branch, let's say, we end up here. Remember that we took gamma negative, so all this is positive. And checking the second derivative, we end up in this expression. Now, because gamma is negative, there is a 0 in this bracket, which means we have an inflection point. And you can show that actually this one is, there is an axis of symmetry at y equal ys, which is the inflection point. Now, the two branches, the plus and the minus, we want to match them at the same position exactly. So we need to have the same values of C1 plus, C1 minus, so that we are talking about the same point. And of course, we want them to have the same images through the two branches, plus and minus. This one gives you, if you hide this part, it gives you a relation between the C2 plus and the C2 minus constants. For simplicity, you can choose ys equals 0 and say that you're going to place the brane at 0, at y equals 0. And that sets the values of the arbitrary constant. So C2 plus will take this value, and it's exactly opposite to C2 minus. And now you can rewrite the solution using an absolute value. This is just the junction condition, the jump of the extrinsic curvature, and the tension that you get. These are just some graphs to give you an idea. This is the plus branch and this is the minus branch. And the next one, I'm matching them in this way. This is minus branch and this is the plus branch. The dashed lines are I'm going to discard the way the solution was constructed. I'm going to use just this part and this part. The reason for discarding those is because I want to find a finite Planck mass in the end. In this figure over here, I just have rotated and flipped. So remember that this was the minus branch, and you have this behavior as y goes to plus infinity. So as y goes to plus infinity, you have the minus branch, and as y goes to minus infinity, you have the plus branch. Now we have to figure out the possibility of localizing gravity. Remember that we have to evaluate this integral. And from the matching solution, you can get the behavior as a goes to 0 is monitored by this term, which becomes dominant. And you can use this to find the asymptotic behavior of a squared. Plug it in the integral. We have used the symmetry of the solution and just worried about negative y. And this is the expression that you get once you calculate the integral. Now, if you let yc approach infinity, gamma, remember, is negative, so this term will go to 0, and you end up with a finite value of the integral. So it is possible to localize the gravity. And for general lambda, for example, for lambda equals to k plus 1 over 2k, where k now can be a positive integer, not equal to 1 that we took it before. The solution can be written, you can prove the form of the solution in this way. And if you look for lambda greater than 3 over 2 that doesn't take this form, then the situation gets a little bit more complicated. You have to do again the to express the integral in terms of the hypergeometric series. So remember, we had this type of integral. The solution we got for lambda less than 1 had specific parameters that were valid for the integral representation. But right now you have to do one-time integration by parts in order to be able to end up with an integral that can have can be represented by the hypergeometric function. And this is the hypergeometric function that we get. So if you have a look at this one, the parameter b is positive for this range, and c is again b plus 1. Now, if you're interested in values between 1 and 3 over 2, the situation gets more complicated. You have to keep doing integration by parts many steps in order to get valid representations of the hypergeometric functions. If you have a look at the range of lambda that I have put here, this one shows that the parameters of the hypergeometric function are as they should be, positive, and so on. So the good thing is we have checked for all other values of lambda, and we have obtained the same behaviors, asymptotic behaviors for A. So A can become 0, it can go to infinity, but at infinite distance. And you can construct a matching solution in a very similar way that we did for lambda equal 3 over 2. And the solutions successfully localize gravity on the brane. So to conclude, we have studied brane worlds with a flat 3 brane in a 5-dimensional bulk that is filled with a general equation of state of this form. If lambda is 1, so you have a linear equation of state, solutions are singular. You can contrast a regular solution, but you have to compromise between satisfying the energy conditions and or the requirement of the finite Planck mass on the brane. For lambda less than 1 and gamma negative, singular behavior persists and the localization is still a problem. For lambda greater than 1 and gamma negative, we have managed to find solutions that are regular, they satisfy the energy conditions, and successfully localize the gravity on the brane. I have given here some, it's a very partial list of bibliography. This is the first paper I mentioned. And this is our first attempt to solve the problem for a flat brane. This is a nice paper that has a matching mechanism with a different bulk matter. And here we have also considered other bulk matters like mixtures or curved branes. This has a matching mechanism, and this is our newest one, which was submitted last week in the archive. And that's all for me.
Okay, thank you very much for this very nice talk. I don't think that we have time for questions here, so we have to move on to the next speaker. Thanks, Evgenia. Thank you again very much.
Thank you.
Okay.
Let me switch off. Sorry.
Yes. Our next speaker is Makoto Narita.
Yes.
And the title of the talk is Strong Cosmic Censorship Theorem in Bakry-Emery Spacetimes. So Makoto, here you are. I'm
Yes.
muting. Thank you so much.
Can you hear me?
Yes, yes,
Yes.
yes.
I start. Yeah. Thank you very much. My talk is Strong Cosmic Censorship in Bakry-Emery Spacetimes. I begin with cosmic censorship. 1969, Penrose proposed weak cosmic censorship conjecture. This means singularities inside black hole. This, yeah, like this. Here is infinity and event horizon and singularity. And this is weak cosmic censorship. After 10 years, Penrose also consider if cosmic censorship principle of nature, it should be formulated in such a way as to preclude locally naked singularities. Then he proposed strong cosmic censorship conjecture. Physically reasonable classical spacetime is globally hyperbolic. Roughly speaking, singularity is not time-like. For example, this is time-like singularity. And this is worldline observer. We can see this is light ray. We can see singularity. Then globally hyperbolic means that there's no time-like singularities. Now, present status of strong cosmic censorship conjecture. We have two ways to prove cosmic censorship. One way is PDE method. Yeah, a famous result is Kristoffer-Kleinerman's stability, nonlinear stability of spacetime. Yeah, Minkowski spacetime, also Schwarzschild spacetime. And spherically symmetric gravitational collapse. Yeah, they are proved this spherically symmetric case. And also cosmological case, Ringstrom, Lenders prove cosmic censorship in Gaudi case something. Another way is geometric method. Mainly, Krorak, Rudolph, Polish mathematicians use this method to prove cosmic censorship. I choose this method. Now, why Penrose proposed strong cosmic censorship? Because he also proved singularity theorem. 1965, Penrose proves singularity theorem for black hole spacetime. This one is also Stephen Hawking proposed 1967 singularity theorem prove singularity theorem for cosmological spacetime. Here, both are physically reasonable spacetime have spacetime singularity singularity means incomplete geodesics. Yes. Roughly speaking, singularity theorems have a basic form like this. Here, there is 3 conditions. One is curvature condition. This means a positivity of matter density. Second is causality condition. Roughly, no time machine, no closed time like geodesics. Also, third condition is initial and boundary condition, a strong gravitational force condition. For example, trapped surface condition. Then space-time should be singular. This is structure of singularity theory. Now, we focus on this curvature condition. I mean, after Penrose Hawking, many singularity theories proved. This means that generalization is these conditions. Now, we focus on this curvature condition. We consider Berkeley-Emery spacetime. Berkeley-Emery spacetime means Berkeley-Emery rich tensor means, for example, scalar field F nu R rich tensor plus Hessian of scalar field. This is a Berkeley-Emery rich tensor. Now, recently, singularity theorem for BER tensor proved by Case, Galloway, Ulga, and Ulga-Weiss. This tensor arises in scalar tensor gravitational theories in conformal gauge. For example, gravitational sector of string effective theory contain not only metric, also fundamental scalar field, so-called dilaton, like this. Then, varying this action, we have Einstein equation like this. Here, Berkeley-Emery rich tensor arises. Of course, if we set like this, we have Jordan-Brunswick form here. In this sense, Berkeley-Emery tensor is generalization of general relativity. Yeah. Now, how to use this condition? We use geodesic focusing. Here we review in GR case. From Rayleigh equation, we can derive this inequality. Here, rich tensor. If time-like convergence condition assume, we have this nonlinear ODE. Then, theta become infinite time. Then, the geodesic congruence has a conjugate point. This is important point. Now, this time-like convergence condition means energy condition like this. This means a positivity of energy density. Then this condition holds for most physically reasonable matter. Yeah. Now, Galloway-Urga prove this similar lemma for Berkeley-Emery-Rich tensor condition like this. Then they proved singularization in Berkeley-Emery spacetime. In this lemma, we have very important result here. In GR case, we have monotonicity, monotonic decreasing of expansion theta. Of course, in Berkeley-Emery case, we have not monotonicity, but if assume this condition, we can prove once expansion theta become negative, then theta stay negative. This is important result. Then we have one question. Strong censorship. We can prove strong cosmic censorship in Berkeley-Emery spacetime. This is our problem. Now, we define naked singularity. Of course, strong cosmic censorship means spacetime should be globally hyperbolic. Globally hyperbolic means Cauchy surface and domain of dependence equal spacetime. This is globally hyperbolic. But this condition is a little bit strong. I mean, for example, this is infinity, time-like infinity. Then, in this case, there is a partial Cauchy surface like this. And here, Cauchy horizon appear. This spacetime is not globally hyperbolic, but there is no naked singularity. In this sense, global hyperbolicity is a little bit strong to prove cosmic censorship. Then we assume violation of causal simplicity. Causal simplicity means J plus causal future of P is closed. This is causal simplicity. Then violation of causal simplicity means there's singularity. In this case, causal future of P is not closed because there's we can go here by causal curve like this. Then we assume violation of causal simplicity. Yeah, of course, we know global hyperbolicity is sufficient condition of causal simplicity, of course. Next, then we assume this naked singularity. It's a bit long. I show you. Partial courses of S and singularity is here and this Cauchy horizon and there is P and generator lambda, past incomplete generator lambda gamma. Also here, this is boundary of chronological past of P here. It's so-called lambda. Yeah. We assume this situation. This is S is properly separated from its future or past Cauchy horizon H process. This we assume this situation. Next, we assume singularity. What's a singularity? Of course, in this case, in incomplete geodesics, but just, for example, just remove a point like this. We have no idea to exclude this singularity. I mean, we cannot prove cosmic censorship in this case. Then we need to assume some condition for singularity. Now we use strong curvature singularity. This is standard Rayleigh equation. I mean expansion equation. Also shear equation. This is standard Riemannian or Lorentzian geometries. Then strong curvature condition is like this, introduced by Clark. I mean, here is singularities and null geodesics like this. And expansion here is negative. Any congruous. Also, future region expansion become positive. Roughly, congruence is like this. This is strong curvature singularities. Then, now we prove strong cosmic censorship theory. Assume strong causality and Berkeley-Emery convergence condition and strong curvature condition. Then, spacetime cannot be future and past nakedly singular related to S. This is our cosmic censorship theory. Now, sketch of the proof. First, here S, and here is singularities. Then Cauchy horizon here, also here. Now we choose point P and construct sequence Pi like this. Also here, this generator is, we call this generator gamma here. Okay. Next. Next, here, this is generator of boundary of chronological past of P, so-called lambda here. And we choose Q here, and this is chronological past of PI. Also, timeline curve law, and we have intersection here. We put this one is QI. Yeah. Then we have this is sorry. This is generator of past causal past of PI. It's lambda I. We can construct null geodesic generator lambda I like this. We can show this segment lambda I converge to lambda also gamma by limit curve lemma. This famous and most important lemma. Then on gamma, neighborhood of singularity, on gamma, expansion theta become negative. Also on lambda, expansion theta become negative. Also on gamma, expansion theta become positive by strong curvature singularity conditions. But this situation is contradiction because we have corollary 1. Corollary 1 means that once sigma negative, then sigma stay negative also. Then this situation is contradiction. This proof is complete. This difference like this. Thank you very much.
Okay, thank you so much for this very nice talk. Are there any questions? We still have some time, a couple of minutes for questions. I have a question myself for you. Your use of the limit curve lemma, this in this particular case, do you have to? Because I think you have to assume that the curves, the sequence are future inextendable, right?
Yeah. Yes.
In this case, this assumption for the Baker, for this R mu nu plus nabla mu nabla nu f, positive. Does this place any restriction for the future inaccessibility of the lambda I sequence of curves?
Sorry. Sorry, I'm not sure, but
I'm not sure because you know, I think if you see the proof, you know, in Hawking-Ellis, for example, the proof, I think there is some kind of restriction to have future inextensible. In your case, can you extend? This I think you can actually, but I'm not sure. I think your proof is correct, but if you, I mean, for the limit curve lemma, in your case, does it hold? It continues to hold, right? Because you don't have anything.
Yeah, I think so.
Yeah.
In our case, we can use standard limit curve lemma. I mean the lemma 621 Hawking-Ellis.
Exactly. Precisely. This is what I'm talking about. Yes. Actually, that proof, it's not. Anyway, that's another point I have about, because as you mentioned in your talk, that's a very important result. This. So you know the proof of Hawking-Ellis is not the same as in O'Neill. I don't know if you notice this. It's a completely different because they have the quasi limits. They have the quasi limits. So that's why I'm asking about the Bakery, the Emery. That's why I'm asking. If you see the proof of in O'Neill, he uses this quasi limit construction, which is not the same as in Hawking-Ellis.
So, but I think energy constant is not the relation to limit curve lemma. I think. Oh, sorry.
No, there is no. Yes, I agree. I mean, all I'm saying is that if you cannot extend, because you relate it to the strong cosmic censorship, some kind of situation. If you cannot extend, you may have some problem applying the hypothesis, the assumptions of this lemma, you know. But I don't think. Anyway, I don't want to waste your time. It was just a thought. Maybe I'm completely wrong, you know. I don't know. But anyway, just because the proof of this lemma is very technical and
yes.
Yeah. Okay. Anyway, thank you so much again. Anyway,
thank you very much.
Are there any other questions? Okay. Thank you again, Makoto.
Thank you.
Bye. Okay. Our next speaker. One second. Is Juan Carlos Rodriguez. Is he here? Oh, hello. Can you please unmute?
Yeah, sorry. Can you hear me now?
Yes. Thank you so much. The title of his talk is Geodesics Near a Curvature Singularity of Stationary and Axially Symmetric Spacetimes. Okay. Okay, thank you so much. Thank you.
All right. Can you see my screen now and my pointer?
Yes, everything is good. Looks good. Thank you.
Well, hello, everybody. My name is Juan Carlos del Águila. Before I begin, I would like to thank the organizers for giving me the opportunity to present my work in such an important event, such as the Marcel Grossman meeting. The title of my talk is Geodesics Near a Curvature Singularity of Stationary and Axially Symmetric Spacetimes. This is a work done in collaboration with Professor Tonatiuh Matos. Well, I will begin by very briefly introducing singularities in general relativity. I will focus here mainly on curvature singularities, and then I will describe the local behavior of geodesics near these curvature singularities. I will focus on axially symmetric spacetimes. The results we derive here will then be applied to the Blavatsky-Demiansky class of spacetimes and to a wormhole with causal geodesic completeness. And at the end, I will give some conclusions. So, well, to this day, singularities are still an open problem in general relativity. These are objects that we do not fully understand yet, and we believe that until we do not have a quantum theory of gravity, we will not have a full grasp of what these singularities mean. Within classical general relativity, there have been a lot of issues when trying to properly define these singularities. Fortunately, today, we know that curves are really useful tools that help us characterize its behavior in a space-time. And in fact, as my last colleague mentioned, there is agreement in considering that a space-time with incomplete geodesics is by all means singular. Curvature singularities are, of course, a type of singularities, and they appear when unbounded curvature scalars happen on a given space-time. In fact, a lot of widely known exact solutions to the Einstein field equations contain them. For example, black holes. However, in black holes, the presence of the event horizon conceals the singularity from external physical observers. But if there is no event horizon present, the singularity is said to be naked. And of course, this situation is pathological, and very often space-time which contain these type of singularities are discarded. The relation between curvature singularities and geodesic incompleteness is not direct, in the sense that curvature singularities not necessarily imply geodesic incompleteness. Examples of these are Wormhole solutions in high energy extensions of general relativity. And the converse, or that is geodesic incompleteness, do not necessarily imply curvature singularities, is given as an example by the Misner model of two-dimensional taub-knot spacetime. This is a widely known model too. So in this work, the question we try to answer is, what determines the existence of incomplete geodesics due to the presence of curvature singularities? To this end, I will make some auxiliary definitions first. Let us introduce a Cartesian or Cartesian-like coordinate system on a four-dimensional pseudo-Riemannian manifold. And let's consider curvature scalar as a map from R4 to R. Then we may define the singular curvature set sigma x as the coordinate values which make the inverse of the curvature scalar vanish. Now, by looking at this definition, one can wonder if it's actually sigma x well defined. And well, for certain cases in general relativity, it is. For example, the Schwarzschild singularity that goes as negative powers of the R coordinate. The Kerr metric is another example. However, yeah, I must warn you here that this definition will not include all possible curvature singularities, since some of them will yield an empty curvature set or a not well-defined one. But in the meantime, let's keep this definition. We also may need to define the neighborhood of a curvature singularity. Now, spacetime is only constituted of regular points by definition, so properly a singularity is not part of a spacetime. So we may not define the neighborhood as easily as with a point that is a regular point. However, this problem can be easily solved by considering a non-isometric embedding from the manifold M to an auxiliary manifold M tilde. This manifold will contain the points of sigma x, thus a neighborhood here can be easily defined. And then we may take the neighborhood in M as the intersection of the points of N tilde with the manifold M. This will allow us to define certain spacetime events that take place in the vicinity of the singularity. For instance, we will say a singularity is time-like if it is generated by a scalar Rx that depends on some spatial coordinates whose coordinate vector fields are everywhere space-like in a neighborhood of the singularity. And will then also be called a time-like neighborhood of the singularity. Now I will focus on actually symmetric spacetimes that gather the following set of properties. They have to be stationary, axially symmetric, and satisfying the circularity condition. This condition is satisfied in a wide range of physically relevant spacetime, such as vacuum, Einstein-Maxwell fields, and scalar fields as well. Its geodesics must also admit a non-trivial quadratic first integral. it must contain a time-like curvature singularity with a non-empty sigma x. And there should exist a non-physical spacetime such that the non-physical manifold contains sigma x and m, and the relation between the physical and non-physical metrics is rated by a conformal factor tau. This we will impose that the tau and non-physical metric are infinitely differentiable in a neighborhood of sigma x in the non-physical manifold, in a neighborhood of the non-physical manifold. All of these properties will carry important implications. The first one is that there will exist an adapted coordinate system such that the metric can be divided into two subspaces. Here I will, the capital letter indices will take values 1 and 2, and the lowercase indices will take values 0 and 3. Also, the metric will depend on the XA coordinates only. And a key to the following analysis is the existence of 4 constants of motion. 2 of them are the P0 and P3, the conjugate momenta, due to the existence of 2 Killing vectors. The third one will be kappa, which will be 0 for null geodesics and 1 for time-like geodesics. And the fourth is yielded by a second-rank Killing tensor, which is given by equation 1. Now, I won't be able to go over all full details of this, but this has to do with the separability of the Hamilton-Jacobi equation, which in certain form imposes a separable structure on the inverse metric tensor. These capital L and theta tensors admit the following decomposition, shown by equation 3. And all of these conditions will allow us to write separated equations of motion. These are shown in this slide, where I have introduced an affine parameter lambda with coordinate velocities .xa. Now these capital psi functions are equated to squared expressions. So only trajectories with psi a positive functions will be possible. I must also note that the sum tau of f and h is positive definite in a time-like neighborhood of n. This is related to the conformal factor of property 4. We can now compute the curvature scalars using the inverse metric I presented. Here, the fx function depends, of course, on the scalar that is being studied, but we can see that its denominator is tau, and according to the definition we made, these can yield curvature singularities in most cases. So we must note if tau has zeros. And the singular curvature set can be written for axially symmetric spacetimes as shown in equation 8, where the B and U3 functions only depend on the XA coordinates, and a point Q in sigma x will follow this same structure. We can now evaluate the equations of motion at a singular point, yielding equations 9 and 10. Here, the quantities alpha and beta, note that they only depend on the conjugate momenta, and they will also depend on space-time parameters such as mass, angular momentum, etc. So causal geodesics will reach the singularity if there exists a set of conserved quantities such that psi is positive for both values of A. Also, since we are dealing with a time-like singularity, and because tau is positive definite, this implies that these factors will be positive too. So with all of these conditions, one can show that both psi A will be positive if and only if the sum alpha plus beta is negative for some real conjugate momenta values. Alternatively, this inequality can be written as inequality 11. So if this sum is negative, then geodesics will meet the singularity. I will call this behavior as sigma encountering. And if the sum is positive, then geodesics avoid the singularity. I will call this behavior as sigma avoidance. However, there is a special case that we must consider, and it concerns the fourth constant of motion. When this quality holds, it can lead to an undetermined limit for the coordinate velocities, especially if it's as I said earlier, tau is equal to 0 at the singular points. So for to analyze this case, a series expansion of the XI functions can help, where the coefficients are given here by equations 12 and 13, as long as the preceding terms of the series vanish. And the logic we follow is similarly as the previous case. However, now if the leading term of the series is odd, then the limit will depend on the path taken to approach the singularity. That means that there will be sigma encountering either coming from greater values of the singular point or lesser values of the singular point. If the leading term is even, then the limit will be well defined, and there will be sigma avoidance or encountering depending on the sign of the coefficients. We can then sum up inequalities 11 to 13 in a general form, is the one given by inequality 14. And we can define this quantity that appears inside square brackets as psi, which will depend of the two conjugate momenta, and establish a first criterion. I show the whole statement here, but it essentially says that there will be sigma encountering if there exists a first non-vanishing derivative of psi, such that either n is odd or the derivative is positive with n even. Now, here we will wonder if geodesic completeness can still be preserved despite a geodesic meeting the singularity. For this purpose, we'll consider the following series expansions. We consider these expressions because they are the ones that appear in the equations of motion. Now we have to determine here which goes to 0 faster, the numerator or the denominator, as the singularity is being approached. So we use the following limit. Note here that there are two variables here, x1 and x2. So again, there will be cases when the limit will depend on the path taken to approach the singularity, so it will be undetermined. However, if the numerator grows fast, approaches 0 fast enough, this limit can be well defined. With this, we can establish a second criterion. Again, it just essentially says that a curve that meets the singularity can be continued after encountering it if enough coefficients of the series in the numerator vanish. These are expressed as a lot of derivatives of the psi function and the non-physical metric. So a curve that for which these conditions hold can be continued and will not become incomplete, at least within the neighborhood of the singularity, provided M contains the feature points of the curve, or at least a suitable extension of M. I am going now to apply all of these results to the Vansky-Demiansky class of spacetimes. The physically relevant spacetimes of this class describe black holes with up to 7 parameters: mass, angular momentum, electric charge, the taube knot parameter, and a Mann-Corrice constant that is only important when L is not 0, acceleration, and cosmological constant. However, I will consider here only those with vanishing acceleration and cosmological constant. This is due because those spacetime for which both of these parameters vanish allow for the integration of null and time-like geodesics. The line element is the following. As you can see, it's rather long and it involves the definition of several functions. However, if we set the appropriate parameters here to 0 and take suitable limits, we can find the well-known metrics of Kerr, for example, Reisner-Nordstrom, etc. And some of its features are that it belongs to a type B in the algebraic classification of spacetimes. It contains event horizons at the roots of delta R, and it has a ring singularity, which is time-like, except for the Schwarzschild case. This slide is meant to show that the inverse metric tensor admits the separable structure that I talked about earlier. and to give the explicit expression of these tensors. Also the functions f and h. Now we apply the first criterion to this class of spacetime. I will focus first on those which have a non-vanishing electric charge. And I have also defined here a new constant of motion, which is in terms of other constants of motion and spacetime parameters. Now, let me explain what the information this table contains. If you recall, the criterion asked for the first non-vanishing derivatives. However, these derivatives will be in terms of constants of motion, and we can choose these constants of motion so that the derivatives vanish. What this table sums up is all the conditions that can happen on the constants of motion. For instance, let's take the first row. We evaluate psi and find this a negative expression. So there will be sigma avoidance unless P vanishes, as well as the four constants of motion. And this has to do with the special case I mentioned earlier that led us to consider the series expansion of psi. We now have to look for first non-vanishing derivatives, and we find that at the second order. And there will be sigma avoidance if we're dealing with time-like geodesics. But what about null geodesics? Well, then we have to continue the derivatives until the fourth order, in which we find a positive quantity. This means there will be sigma encountering. However, the conditions for this to happen are P equal to K, equal to kappa, equal to 0. And this condition, in fact, constrains geodesics to the plane of the singularity. And these are the principal null rays of the spacetime. Now, let's consider those spacetime with vanishing electric charge and positive mass. The main difference between this table and the last one is that here we don't have to impose any condition on the constants of motion in order for the derivative to vanish. Hence, there will be sigma avoidance unless P equals to K. However, now the first non-vanishing derivative is of first order. This is an odd order, so there will be sigma encountering coming from positive values of R, or sigma avoidance coming from negative values of R, which these are obtained by performing a maximal extension of the spacetime. The following rows are just like the previous case, so I won't explain them. Now we will consider a family eta of principal null rays, which, as I said, are defined by P equal to 0 and K equal to 0, and are null geodesics. The second criterion asks for a lot of derivatives on physical metric. I show the computations here, and as you can see, it involves always the P quantity, but for our case, P equals 0. So we can see that conditions of criterion 2 are satisfied. And this seems to suggest that there is no incompleteness in these curves, at least due to the singularity. It is noteworthy to see that these tangents are aligned to the principal null directions of the spacetime. Recall that this is a type D spacetime, so there are two null directions twice repeated, and they represent ingoing and outgoing null geodesics. Now, one last example is provided by this wormhole with causal geodesic completeness. This is a wormhole that was roughly based on previously found ring wormholes. Here, however, the line element is obtained somewhat artificially. And what I mean by this is that it was based on geometrical arguments, so that there is always sigma avoidance for the spacetime. However, the gravitational source that can yield this spacetime may not exist. However, this can be seen as a nice exercise to consider. And the line element here is also rather long. I used of late Sprolai coordinates to express it, which can be then expressed in terms of Euler-Lindquist coordinates, and has a length parameter and an angular momentum parameter. It also involves these delta functions. This will be important then for the curvature singularities of the spacetime. However, it could be more illustrative to embed this spacetime into three-dimensional Euclidean space. I show here the profiles obtained and show that indeed this spacetime has a wormhole geometry. The Ricci scalar of this spacetime is given here, and it contains two quantities, delta and delta S, that can yield curvature singularities, and in fact they do. However, they have completely different properties. This sigma singularity yields a ring singularity very much like the Plebanski-Demiansky case. However, sigma prime now will have consist of a two-manifold cross R or cross time. This singularity will be defined by two circles in the xy plane, whose radius depend on this parameter A over L squared. And in fact, if set parameter is less or equal than 1, then the singular curvature set will be homomorphic to a torus cross R. Or if A over L squared is greater than 1, it will be a two-sphere cross R. To show this, I present here the set sigma prime x in a plane U1, U3. Here, U1, U3 are Cartesian coordinates, and U3 is the symmetry axis. So these profiles should be rotated about this axis to obtain the topologies I just described on sigma x. And well, there are a lot of cases. We will later consider a case in which the angular momentum is very small, which shrinks the singularity to a neighborhood of the ring singularity. This table is for the ring singularity only. The logic followed here is the same as the Plebanski-Demiansky case. So we can see that there will be sigma avoidance unless all of the constants of motion are set to 0, which implies that the coordinate velocities vanish as well. And this is trivial motion and can be considered as unphysical. Hence, we conclude that no causal geodesic meets the ring singularity. However, there was another singularity, the sigma prime. If we consider a slow rotation limit that is achieved by setting the parameter A over L squared to much smaller values of 1, then the region sigma prime shrinks to a neighborhood of the ring singularity, which we already proved to be inaccessible to causal geodesics. If A over L squared is greater than 1, then there will be sigma encountering, because there will be points Q prime in sigma x prime that will make the psi function positive. So we can conclude that a slowly rotating wormhole described by metric 19 will be a spacetime with causal geodesic completeness despite the presence of curvature singularities. Finally, in this work, we have formulated a set of criteria that regarding causal geodesics and curvature singularities. The first criterion deals with the behavior of nearby geodesics in the curvature singularity, and the second established the possibility that maybe the curvature singularity is not an obstacle to completeness. These criteria were later applied to some metrics of Plebanski-Demiansky class of spacetimes. Here we found that in the electrically charged cases, the singularity is only reached by the principal null rays of the spacetime. In the uncharged ones, unfortunately, there will be time-like annual incomplete time-like annual geodesics in contact with the singularity. And finally, our results seem to suggest that the principal null rays do not become incomplete near the singularity. Finally, I presented here an example of a causal geodesically complete wormhole, despite the presence of unbounded curvature. And that will be all. Thank you for your attention.
Okay, thank you so much for this very nice talk. Are there any questions for Juan Carlos? Can I ask you something? If you have normally to have a stable wormhole, you need to have some kind of exotic matter, you know, some fluid with negative. Now, in your case here, this completeness, is it, you have any guess as to what would happen if you have some matter, you know, will remain this causal completeness?
Okay, yes. So yeah, it is known that to support a wormhole's road, we need exotic matter. Well, as I said, this example was constructed based on geometrical argumentation. However, I do suspect that this wormhole has to violate some energy condition, and the stability of it, well, like it is a completely different subject. I will not venture to guess something.
Yes.
But yeah, the completeness, if it were stable, yeah, I will not guarantee that completeness will still remain, but that's a really interesting question, and of course, it's in order for us to consider a reasonable matter, all of this has to be taken into account, of course.
Yes.
So yeah, I cannot unfortunately answer that question directly here, but
I think there are some very easy stability criteria. You know, many years ago, if I remember correctly, by Beam and Ehrlich, they had done some kind of stability of geodesics. You can find them in their book, you know, this global Lorentzian geometry. They have some very simple thing, very nice result actually, about the stability of geodesics. So instead of doing the problem again from the beginning by adding matter,
yes.
maybe you can just see whether your complete geodesics are stable in their sense. You know, maybe it would work. But it's a
Okay,
very interesting result, this, I think. Yeah.
Yes. Thank you for that comment, actually. Yes.
Okay. Are there any other questions? Okay, Juan Carlos, thank you so much again.
Thank you.
Okay, our last speaker now is Deborah Konkowski. Here she is. Okay, hi Deborah again. The title of her talk is Open Problems in the Nature of Singularities in Relativistic Spacetimes. Okay.
Okay, I think it's up here.
Yes,
Let me get to the first page. 1 second, I don't think it's working quite right.
Yes, it's good. Everything looks good.
It looks good.
Yes.
It won't let me change pages though.
Are you sure?
Yeah. Let's see, now it will. Okay, I'm okay. Okay, this is the beginning. Okay, I'm going to talk about open problems and understanding singularities in general relativistic spacetimes. And here's my outline. I'm going to first talk about singularities, classical, like we have been discussing, and then also a description of some quantum singularities, which are based on the classical, and then some examples of both in power law spacetimes and self-similar spacetimes, and then a little discussion. And as I go through these, I want to talk about unsolved problems that we need to consider in each case. So a spacetime is a manifold and a metric. The manifold is smooth, C infinity, paracompact, connected Hausdorff manifold, and the metric is a Lorentzian metric. For classical singularities, we often talk about the spacetime as being smooth. So a singular point, as has been noted, has to be cut out of the spacetime. It leaves holes, incomplete curves, and boundary points. So how do we define a boundary to a spacetime? Well, we take the spacetime and we add on a boundary. It's impossible to take Cauchy completeness, which works only with Riemannian metrics, not Lorentzian. So how do we complete spacetimes? There have been many boundaries posited in the past, and those include the abstract boundary by Scott and Zekaras, B, the bundle boundary by Schmidt, C, the causal boundary by Garrosh, Kronheimer, and Penrose, and G, the geodesic boundary, which is Garrosh's. And that's the one that talks about geodesic incompleteness. Now, there's one slightly newer boundary also by Lowe, I boundary, and it was motivated by Penrose's twister program. What it does is take boundary points representing future endpoints of all null geodesics that can be considered to form the future light cone of the boundary point. And it's related to the earlier C boundary, the causal boundary, and has some of the same problems. Many of these boundary, all the boundary descriptions that I know of have problems. Sometimes they will identify future and past infinity, or have other major problems with exact solutions. And then there's a related question, which is exactly what I just said, which is, can we now describe or construct a really good boundary description? So if anyone's into putting all those descriptions together and getting one that works really well, that would be great. So what about classical singularities in this talk? Well, I'm going to take it to be Garrosh's definition, which is a singularity is indicated by incomplete geodesics or incomplete curves of bounded acceleration in a maximal space-time. And there's a related question to that also that Professor Malcolm McCallum pointed out, which is to show time-like and null geodesics really are the idealized paths of massive and massless particles. It's assumed, but it's not been proven. How about the singularity theorems? Well, we know those were described by Hawking and Penrose from 65 to 70. The basic assumptions include generic condition, a generic condition, an energy condition, and a causality condition. And the conclusion came out to be that if you have a closed universe, a black hole, or our universe with its matter content and black body radiation, there will be geodesic incompleteness, and that's taken to mean a singularity will occur. But what it really says is geodesic incompleteness. So we'd like to modify the theorems to reduce assumptions like people have been trying to do in this talk, and also simplify types of or nature of the singularities with the definition of geodesic incompleteness. So what about different types of singularities? There's a good classification scheme way back from 77 by Ellis and Schmidt, which takes a singular point. They were using a B boundary, but it doesn't really matter. Just consider a point that has incomplete geodesics going to it and is not at infinity. It's a finite distance one. Does the Riemann tensor's kth derivative diverge in some parallel propagated orthonormal frame? If the answer is no, you've got a quasi-regular singularity. If the answer is yes, there's a curvature singularity. Then you ask, how about scalars in the Riemann tensor and its derivatives? If the answer is no, the scalars do not diverge. You have a non-scalar curvature singularity. If the answer is yes, scalars do diverge, scalar curvature singularity. Examples of those are the standard ones. Quasi-regular would be conical singularities, idealized cosmic strings, dislocations and disclinations in spacetimes, and the folds in colliding wave solutions. Non-scalar curvature singularities could be whimpers, some plane wave types, type 5, locally rotationally symmetric spacetimes. Scalar curvature singularities are the ones that we're most familiar with: big bangs, black hole centers, big crunches, most future collision regions of idealized gravitational waves. And questions, lots of questions arise from all of this. Are there more examples of different kinds of singularities or different variations on the ones we've just talked about? What's the relevancy in particular of those that are very mild? How about exact solutions? Where do we find which ones? Realistic matter, what can appear if the matter is actually realistic and is not some sort of exotic matter? And how about which ones are generic? And there's great references. So there's a Hawking and Ellis book, Ellis and Smith's paper, and Professor McCallum had a paper back in 2015, which talked about space-time invariance. Now, what about quantum singularities? This is something we don't usually talk about. What if we use quantum waves instead of classical geodesics in order to identify the position of a singularity? So if we use classical particle paths, time like a null geodesics, instead of those, if we take quantum mechanical particles, quantum waves, and use those to look at the singularity. Well, this was first discussed mainly in 1995 by Horowitz and Maroff. They talked about a spacetime as quantum mechanically non-singular if the evolution of a test scalar wave packet representing a quantum particle is uniquely determined by the initial wave packet, the manifold, and the metric, without having to put any boundary conditions at the singularity itself. That's very unusual. So technically what they're saying is a static spacetime, so we need a static spacetime, and this actually usually refers to time-like singularities. So we've got a static spacetime as quantum mechanically singular if the spatial portion of, say, for example, the Klein-Gordon operator, it's probably the simplest one to use for a wave operator, is not essentially self-adjoint on C0 infinity in the space of square integrable functions. So what does self-adjoint mean? We're all familiar with that just from physics. So the definition of self-adjoint operator, briefly, a densely defined linear operator A on a Hilbert space is self-adjoint if it equals its adjoint. That is to say, A is self-adjoint if first, the domain of A coincides with the domain of the adjoint, and two, the operator A agrees with its adjoint on this common domain. Then how about essentially self-adjoint? Because that's what was used in the description. Well, a symmetric operator A is always closable. That is, the closure of the graph of A is the graph of an operator. A symmetric operator A is said to be essentially self-adjoint if the closure of A is self-adjoint. Equivalently, A is essentially self-adjoint if it has a unique self-adjoint extension. So what do we use in order to figure out if an operator is self-adjoint? Well, there's a von Neumann criteria of deficiency indices, which you may have learned if you took any courses in functional analysis at any point. And there's also something called the Weil limit point limit circle criterion, which is what I'm going to use now. And that comes from the Reed and Simon books. What they talk about is Weil limit point limit circle criterion relates essential self-adjointness of the Hamiltonian operator to the behavior of the potential in an effective one-dimensional Schrodinger equation. It's not a real Schrodinger equation. It's made from the Klein-Gordon radial equation. It's just the form of the equation looks sort of like a Schrodinger equation, which in turn determines the behavior of the scalar wave packet. So what you do is you take the Klein-Gordon radial equation and rewrite it in the right form, which has the form of h psi equals e psi, where the operator h looks essentially like a second derivative operator plus a potential, and E is a constant, and the singularity is taken to be at x equals 0. So in Reed and Simon, you'll get a definition. It says the potential is in the limit circle case at x equals 0, if for some and therefore all E, the solutions of h psi equal e psi are square integrable at 0, otherwise at infinity. If V of x is not in the limit circle case, it's in the limit point case. If it's limit circle at the boundary if it's limit circle, what we would need is a boundary condition at x equals 0 to have a unique solution. If it's limit point, we actually don't need a boundary condition to specify a unique solution. That's the whole idea behind quantum singularities and non-singularities. It's non-singular if you get a unique solution without putting in the boundary condition at the singularity. And there's a theorem from over 100 years ago by Weil, which says that V of x is a continuous real valued function on 0 to infinity, then the Hamiltonian is essentially self-adjoint on C0 infinity, if and only if V of x is in the limit point case at both 0 and infinity. There is a useful theorem in Reed and Simon that can be used, and it satisfies limit point for all the spacetimes we're going to consider here. So we're not going to worry about infinity generally. What we're going to worry about is near x equals 0, near the singularity. And that has a great theorem that's useful from Reed and Simon. And it says, let v of x be continuous and positive near 0. Then v of x is in the limit point case if for some epsilon greater than 0, v of x is less than or equal to a term x to the minus 2 near 0. And in that case, v of x is in the limit circle case. Thus, the potential is only limit point if it's sufficiently repulsive near the origin. If one of the two solutions of the one-dimensional Schrodinger equation blows up so quickly that it fails to be square integral. So let's keep going and look at some examples. So there are some example spacetimes. There's lots of example spacetimes you can look at. One sort of general class, which is fun to look at, is power law spacetimes. We looked at this in the late, like 2008, somewhere in that range. And what we figured out was the following. We took a class of spacetimes that had power law metric form at small r. So we had r to the alpha times dt squared and r to the beta times dr squared, a constant to the minus 2 r to the gamma d theta squared, and r to the gamma delta squared, or r to the delta dz squared. And we're in the limit of small r, and these constants were parameters, and the t, r, theta, and z had the usual ranges. And we were really concerned about small r because we thought that if there's going to be a singularity, it's going to occur at r equals 0. So what we did was we eliminated alpha by scaling. Alpha was the coefficient of the r term in front of the dt squared. And by scaling, we got two types of spacetime. We got type 1 and type 2. First type was alpha not equal to beta plus 2. The second type was alpha equals beta type 2. And I'll explain both now. Okay, so except in isolated values of the parameters of these power law spacetimes, they all have diverging scalar polynomial invariants if and only if beta is greater than minus 2. And Lake in 2008, so we must have been maybe a little bit earlier than that, 2007, showed the following. Type 2 spacetime singularities at r equals 0 are null, naked, and at finite affine distance. So they're classically singular. And type 1 spacetime singularities at r equals 0 are time-like, naked, and at finite affine distance. If and only if beta is greater than minus 1. And they're classically singular at r equals 0, only if beta is greater than minus 1. Okay, so keep going. So we did our technique, which was take the spacetimes, divide them into a spatial time-like part and a space part. So look at the operator on the space part, get the Schrodinger form of the radial equation. So we had the radial equation, look at square integrability of solutions, see if we had a unique solution, and see what happened. And what you can do is show first that there's no singularity in the type 2 spacetimes. Type 2 spacetimes actually are globally hyperbolic. The wave operator in that case is essentially self-adjoint. So these spacetimes contain no quantum singularities. And it's easy to verify that congestion directly by checking essential self-adjointness using the wave operator. So you can do the whole calculation, but it's not necessary at all. And how about type 1 spacetimes? Well, in type 1 spacetimes, actually, I'm going to consider beta equals minus 1 as the base plane, because beta equals minus 2, it's not actually classically singular completely. So we'll take beta equals minus 1 as the base plane, and then we'll take a couple sides. And everything inside the bowl is quantum mechanically singular, and everything outside the bowl is quantum mechanically non-singular. Okay, so it's interesting. And you can also look at energy conditions. And type 1 spacetimes, certain ones depend on Well, it depends on the parameters as to whether you get weak or any of the conditions are satisfied in any cases. So type 1 spacetimes with -2 less than beta, less than or equal to -1 are entirely eliminated if either the weak or the dominant energy condition is invoked. And those were the spacetimes that are non-singular anyway, since they're geodesically complete. For any other finite values of beta, there's a range which satisfies the weak energy condition, and nearly always smaller but non-zero range of parameters which satisfies the dominant energy condition. Although neither energy condition is completely helpful in eliminating the quantum singularities from the power law spacetimes. Now, the question of energy conditions is interesting in some cases because, you know, the Casimir effect means that local negative energy densities are possible. So it's a question of, do we want to keep the energy conditions or not? But generally, we cannot eliminate the quantum singularities just by using the energy conditions. So a large class of the classically singular power law spacetimes we have examined is quantum mechanically non-singular, but then there's also a class that's quantum mechanically singular. Conformally static spacetimes, the ones we had looked at and the theorems that had been talked about had all had to do with static spacetimes. So we decided to maybe try generalizing things and go to conformally static. And so we looked at conformally static spacetimes. The idea came from Ishibashi and Hosoya, who had looked at conformally coupled scalar fields and inner products for wave regularity on spacetimes. And so we looked at general coupling using the Klein-Gordon equation. You can also use Maxwell equations. You can use Dirac equations in both static and non-static, in both static and conformally static. They're just much more complicated and they give you similar results, but different parameter ranges in general. So for conformally static metric, we just had to take a slightly different square integrable function definition, but we could do the same kind of calculations. And we rewrote things using Klein-Gordon radial equation in the one-dimensional Schrodinger form. We had a Hamiltonian operator and an energy as a constant. And we took the singularities to be at x = 0, and then determined whether the potential was limit point or limit circle. So we were using the same theorems, basically. And the technique was basically identical to what we had done before. So what we looked at for these conformally static spacetimes was a nice class of self-similar spacetimes. And those were given by Brady in '94. And these self-similar spacetimes had a conformal factor, e to the 2t, and then the metric had a G1 and a G2, which were arbitrary functions. The spacetimes themselves were conformally static and self-similar. G1 and G2 could be arbitrary functions, but here for simplicity, what we did was take them to be G1 was x to the p, G2 x to the q, so they were just power log n. And these spacetimes all had time-like scalar curvature singularities in the cases that are defined below, q greater than 0 in that range of p at x = 0. And our conclusion was that the only values in p and q that led to potentials in the limit point case were very restricted, and all others were limit circle. And therefore, no scalar curvature singularities in this class of there's no sort of generic class of scalar curvature singularities of these self-similar spacetimes that's healed quantum mechanically. So we're not getting healing like we did in that nice case, the power law, where we actually did get, let's see, let's just go back to it. In the power law conclusion, there was a whole range in that bowl, inside the bowl, where they were quantum mechanically non-singular. So it would be nice if by throwing quantum mechanics in, somehow we could come out with something that would take out some of the classically singular spacetimes that exist. But we're not it hasn't worked that well completely. But what would be nice to do at this point is maybe do a classification scheme for these quantum singularities, see if we can relate that classification scheme to the classical singularity types, It's not relatable at the moment. We tried just a regular idealized cosmic string with a quasi-regular singularity. It's still singular quantum mechanically, unfortunately. Look at more examples and answer the question, when are classical singularities invisible to quantum waves? And most importantly, is there any way in the world to be able to maybe this be a baby step towards coming to some idea about where there is a quantum theory of gravity? One goal for the future is to understand more comprehensively and more deeply which singularities can be resolved using the quantum singularity method and which cannot be, and why. And here's just a brief history of quantum singularities if anyone's interested. Wald really started out the whole thing back in the 1980s. Horowitz and Marov built on that and got the whole idea of quantum probes of space-time singularities in 95. Ishibashi and Hosoya generalized to finite energy waves, which is different than the way we've been doing it because we've been doing just regular square notability, not using a finite energy wave description. And there are review articles. Patelli and Letelier did quantum singularities in static spacetimes around 2010, published 2011. We did one about the same time, also published 2011. I worked with Professor Hellawell at Harvey-Mudd College in Claremont, California. And we have a more recent paper also on review of singularities in modern physics letters in 2018. Now, I forgot to put on a thank you note, so let me say thank you and also thank the organizers for letting me give the talk. Thank you very much.
Okay, Deborah, thank you so much for this very nice talk, which raises actually many questions, I think, at least to me, which I would like to ask you a couple of things.
Okay.
Well, are there any questions, first of all, by someone else, if you would like to ask Deborah something? Well, let me start. If someone else thinks of something, you can ask. Can you go back to this slide with the power law, what you call the power law metric of where you have the power law space times with a R to some, yes, there. Okay. I mean, there after this, when you have these two cases where you said you take out the R to the power B, okay, or sorry,
R to the alpha is the one that
R to the alpha. Okay. What do you do with the R to the alpha? What do you do?
It's absorbed into the T. And alpha is not equal to beta plus 2.
Because you know what I thought, if you go back to the previous slide, if you take out, actually, if you take a common factor R to the A outside.
Oh, then I get conformally.
Exactly. This is what I thought, because well, one thing is to redefine the time as you did, but the other thing is to go to the conformal class where
great. That's a great idea. I didn't think of that.
You know what I mean? Because the other conformally static case you had,
right,
the conformal factor is never 0.
Whereas
in case
this one is.
You know?
Yeah, that's right.
So
yeah, because the other conformal factor is e to the
Yes, that's why. So it never vanishes, you know. So
right.
in this other power law case, I think it's more interesting actually, because you can take a conformal factor to the left-hand side and have the conformal class of space-times where actually the factor you might consider suitable limits to infinity or to 0, depending on what alpha is.
Right.
So I think this would actually, what you have is to compare with the quantum case. In this case here, if you go to the conformal class, I think, I'm sorry. I think you would have more general results actually.
Oh, that would be great. That's a great idea.
Yeah, because I mean, you know, you can modulate somehow the behavior of the whole class by taking special cases for alpha. Because the conformal factor, if alpha is positive or something, it will go to 0, if negative will go to infinity. So you would have,
Right.
yeah, I don't know, that might be an interesting topic to do, you know.
That sounds really interesting. Sounds great for this summer, actually.
Yes, yes, something like that. I don't know. Okay.
I just retired, so I actually have lots of time.
Yeah, yeah, okay.
Okay.
Very good. Okay. Any other questions for Deborah here? Okay, thanks again for your very interesting talk.
Thank
In
you.
fact, thank you all for coming. It was a very interesting meeting, very, very beautiful, good ideas, new ideas. So I hope to see your papers when they are published in the proceedings. I don't know when that actually takes time in the Marcel Grossman meetings. So I think, yeah, well, I hope you all write papers, contributions. Okay, nice to see you all. Have a good evening. Bye-bye.
Yes. Thank you very much. Yes.
Bye.
Thank you.
Bye. Thank you.
Bye, thanks. Thank
Bye-bye.
you.
Bye-bye.
Bye.